Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, we're going to start into the graphs of polynomial functions as treated as if you were straight out of an an Algebra 2 course, which is intermediate algebra. So we'll kind of cover some of the big topics in graphing polynomial functions, but we won't cover every topic. There's some topics we're going to reserve for pre-calculus here. The very first thing we're going to talk about is just common characteristics of graphs of polynomial functions. And there are some calculus concepts here, specifically the idea of a function being continuous. So graphs of polynomials have two main characteristics. They're smooth and they're continuous. So let's talk about both of those concepts. When I say a function is smooth, that means that when you draw it, it has a nice smooth curvature to it. It's not as if it does something like this. So that's a polynomial, but it's not as if it does something like this. Okay. Notice this point right here. That is known as a kink or a corner or a cusp. And those are explored a lot in calculus, but not in college algebra or pre-calculus. But the main thing you need to note here is, again, that these functions have this nice, smooth, kind of lazy little flow to them. Although if you do get high degree polynomials, they do have some quite crazy behavior. They can do something like that, for example. But that's if they have very high degree. Generally speaking, we're going to be dealing with low degree polynomials in this course, or at least in these videos. The other characteristic is that polynomials are continuous. Now there's really one true definition of continuity, or that a function is continuous, but at this level in college algebra and in pre-calculus, a lot of students will hear that a function is continuous if you can draw it without lifting your pen. And so there are a lot of functions that are continuous. This function right here would be considered to be continuous, right? Because I drew it without lifting my pen. Now, I will say, for any mathematicians that will ever watch this, that is a lie. There are some very theoretical functions that are continuous at specific points, yet you lift your pen an infinite amount of times to draw them. However, that's a calculus concept. For us right now, just consider a function to be continuous if you can draw it without lifting your pen. Just know that's a flawed definition. Now, when you're handed a polynomial function, often you're going to be asked to evaluate it or to graph it. And I should say, I really want you to drive home the point that polynomials are kind of the end-all be-all of all functions in mathematics. You wouldn't think so. They're like the simplest functions you'd ever encounter, like 3x plus 7, that's a polynomial. Or 3x squared plus 7x plus 5, that's a polynomial. And it turns out that we in mathematics would love to have all of our functions written as polynomials. So we spend quite a bit of time in your undergraduate career researching them, making sure that we know everything we possibly can know about them, because eventually you'll find out almost every single function that you ever encounter, whether it's an exponential function, e to the x, or a natural logarithmic function, or a sine function, all of those functions have polynomial representations. And it's much easier to work with polynomials in the real world than it is to work with sinusoidal functions or exponential functions, so we prefer to work with polynomials. That being said, let's talk about the zero of a function. So if c, the number c, is in the domain of a function, and if f evaluated at c turns into 0, then c is called a zero of the function. I want to give you a little bit of warning here. A zero is a value that turns your function into zero when plugged in. It's not that you're plugging zero in. For example, let me just make something up here. Consider the function f of x is equal to the quantity x minus 1 and quantity squared. 1 is considered to be a 0 for this function because f of 1, which is equal to 1 minus 1 squared, which is equal to 0 squared, which is 0. Well, when you plugged 1 in, you got out 0. That implies x equals 1 is a 0 because you plugged it in and you got out 0. However, if you were to plug in 0, this is 1. So 0 is not a 0 for this function. Let me say that again. X equals 0 is not a 0 of this function. And again, that's because when you plugged in that value, I don't care what the value is, but in this case, we plugged in 0. And if it doesn't return a 0, then that value is not a 0. We plugged in 1, however, and when we did that, it returned a 0. Therefore, 1 is considered a 0 of the function. So very, very important that you make that distinction. A lot of students initially think that when I ask for a 0 of a function, they want me to plug in 0. No, I don't want you to plug in 0. I want you to find a number that you would plug into your function that would return a 0, that would cause your function to become 0. Now, if you think about a graph of a function, if I told you, for example, with this function right here that I'm making up, I'll just call it f, and let's pretend this is a value of -5, x value of -5, that is. This is x value of 1, and this might be an x value of 3. I hope you would agree that f evaluated at 1 for this curve that I've drawn out here should be 0. Because, again, when I plug 1 in, I get out 0, a y value of 0. So when I tell you we have a 0 at -5, 1, and 3, I'm also telling you the graph of our function has x-intercepts at -5, 1, and 3. And that actually brings up our first theorem related to zeros of a function. The zeros of a function occur at the horizontal intercepts of the function. I'm not going to prove this, although the justification is very easy, right? And that's just because if you know that f of c is equal to 0, then you know that c comma 0 exists as a point on the graph of the function f. And that implies x equals c is an x-intercept. Well, now I've actually just proved it. So there you go. We now know that if I tell you have a 0 at 5, that means 5 is also an x-intercept for your function. Zeros and intercepts, they go synonymously hand in hand. There's also another word that kind of goes hand in hand with zeros and intercepts, x-intercepts that is. Roots. A lot of people will say you have a root at c. You have a 0 at c, you have a root at c, or you have an x-intercept at c. They all kind of mean the same thing. There's subtle differences between them, but for our purposes, they all mean the same thing. So let's take an example here. Let's go ahead and find the zeros of this function. To find the zeros of a function, you would like to find out actually where the x-intercepts are. So that's why I introduced that last theorem. To find the zeros, you could hunt around for quite some time. You could say, let me see what I could plug in to turn this into 0. You could totally try that. But that's not going to work very well here because there are an infinite amount of numbers that you could try to plug in. And in fact, that's a great way of viewing this. You don't want to try to plug in an infinite amount of numbers. You'll be here for the rest of your life. So instead, you would prefer to find the x-intercepts. And you should know, because you have passed through all of the algebra sequence, that finding x-intercepts is the same thing as setting y to 0 and solving. So let the output, p of x, equals 0 and solve. So let's go ahead and do that. I'm going to let the left-hand side equal 0. We have 0 is equal to 3x cubed plus 7x squared minus 12x minus 28. There are 4 terms on the right-hand side of that equation. So I'm going to do a factoring by grouping. I'll group this together and group this stuff together. In that first group, well, you can factor out an x squared, and you're left with a 3x plus 7. In the second group, you can factor out a negative. Let's see, they're both divisible by 4, so I'll factor out a negative 4. If you divide that by a negative 4, you get 3x. If you divide that by a negative 4, you get a plus 7. Notice both of the terms that we have now have a 3. Oops, that's not what I wanted to do. They both have a 3x plus 7. So I'll factor out a 3x plus 7. All of those years spent factoring, and here you are finally using it for a purpose, right? And you're left with an x squared minus 4. And of course, x squared minus 4 is a difference of squares. So that's going to be 3x plus 7 times x minus 2 times x plus 2. And now we can use what's called the zero factor property, which just tells us if you have the product of objects, I'm saying objects, it's really expressions, but if you have the product of objects and it becomes 0, then one of those things had to have been 0. So if you take 3 things and multiply it and it becomes 0, one of those 3 things at least had to be 0. So I'm going to say this implies either 3x plus 7 is 0, or could have been the x minus 2, or it could have been the x plus 2. And in the first case, you get x is equal to negative 7/3. Second case, you get x is equal to 2. Last case, you get x is equal to negative 2. Those are the values of x that cause this function to become 0. So those are the zeros of this polynomial function, because again, they're the ones that you would normally plug in. You could test it out, by the way. Plug in 2. 2 is probably the easier of the 3 numbers. If you plug in 2, right here you get 2 cubed, which is 8, times 3, which is 24. Plug in 2 to this, you get 4 times 7, which is 28. Well, we have a minus 28, so that's going to disappear. Right? And then again, you're plugging in 2 times a negative 12, so that's a negative 24. So 24 minus 24, 28 minus 28. Yep, that turns into 0. So 2 must be a 0. And in fact, it's just my way of saying all of these are zeros of that function. And because I'm trying to make these videos somewhat short and digestible, I think that's pretty good for now. So we've, in this video, just talked about the factoring, using factoring to find zeros of a polynomial, and we just needed the one example to really do it. So there you go. If I hand you a polynomial and say find the zeros of a function or of that polynomial, all you need to do is factor it. I will say that as you move forward in mathematics, the polynomials you face get more and more complicated, and you have to invent new methods to factor them, because once you get beyond these 4 terms, it becomes more of an art form to find the factorization. And that's a pre-calculus topic. But I'm just letting you know, in this course, we'll deal with kind of easier polynomials to factor. But as you move into pre-calculus, you get, I think my pre-calculus students right now are dealing with polynomials that have 8 terms in them. And to factor something like that, you require specialized theorems to help you out. So you get to look forward to that. All right. That's all I have for you in this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.